In this video, I'm going to present a summary on the technical report Nomic Embed, Training a Reproducible Long Context Text Embedder by Nomic AI and Cornell University. I have 5 sections in my presentation. I'm going to start with main takeaways, then walk through the 3 training stages and the data used in those stages, and this is going to be the bulk of my presentation. I'm going to talk about consistency filtering and then go into results, and then I'll end with Dynamic NTK Scaling. So these were the 9 main takeaways I had from this report. First of all, and the most impressive one, and I think the most impactful one, is that Nomic Embed Text v1, which is a 137 million parameter model, is the first fully open in terms of weights, code, and data, state-of-the-art embedding model. This model was trained in 3 stages, and they have various other models that are related to those stages. They use consistency filtering to improve data quality and reduce training compute. And nuance or detail is that top K was better than cosine similarity threshold, which we'll talk about. They use contrastive fine-tuning with in-batch and hard negatives. They find that single source batches prevent source shortcuts in terms of the model using shortcuts based on patterns in the batch. They use task-specific prefixes to improve model performance so that it understands different behaviors based on different tasks. The Nomic Embed Text v1 model outperforms both OpenAI Ada-002 and OpenAI Text Embedding 3 Small on short context and long context benchmarks. They achieved this long context of 8,192 tokens while only training on a 2048 context length by using what is called Dynamic NTK Scaling. And they use modern optimizations to improve training performance. So let's dig into training stages and data. There are 3 training stages involved. First is masked language modeling, and the outcome of this is the Nomic BERT 2048 model. Then they use that to initialize their weakly supervised contrastive pre-training stage, and from that stage you get the Nomic Embed Text v1 unsupervised. And then the third stage is supervised contrastive fine-tuning, from which you get the final Nomic Embed Text v1. So let's start with stage 1, masked language modeling. This is where they mask a percentage of inputs, and they train a bidirectional transformer to predict the masked tokens. They tokenize the training documents using BERT base uncased as their tokenizer, and they pack across documents to chunks of 2048 tokens. They deviate from the original BERT training method by omitting the next sentence prediction task. The 2 datasets they use for their first stage of training is books corpus and a 2023 Wikipedia dump. In terms of those optimizations that I was talking about, here are the changes they made to BERT base. They're using rotary positional embeddings. They're using SWIGLU instead of GLU, and that gave them a 25% speed up. They're using flash attention, a dropout of 0, and they're using a vocab size that has a multiple of 64. So that's stage 1. Stage 2 is weakly supervised contrastive pre-training, and the weakly supervised is that they're using large collections of publicly available data to form these contrastive pairs. They start out with 470 million pairs across 29 data sets, and these are all sorts of different pairs of data that you can find across the internet, and we'll look at some details in a second. They use consistency filtering to filter that 470 million data set down to 235 million. They create long context pairs using Wikipedia articles and research paper abstract body texts. The training in this stage is initialized with the final model from the last stage, which is Nomic 2048. They append task-specific prefixes to queries and documents to help the model distinguish between task behaviors. And they fill batches with the data from the same source. So this is the 4 different task-specific prefixes they use. They have search query, search document, classification, and clustering. And they have 2 types of prefix categories. They have symmetric, where the query document have the same structure, and asymmetric, where the query is usually a single sentence, and the document can be many sentences, such as a search query, search document. And the search query document pair of prefixes are used for retrieval, and then they have classification and clustering. I had a conversation with Claude, multiple conversations with this paper provided as the project knowledge. And one of the highlights I want to just add from that conversation is about using single source data in the batch. And so the concept there, from what I understand, is that if you mix multiple sources of data within the same batch, the model is going to learn to recognize task behavior based on source data structure. So if you have a Reddit post mixed in with a textbook snippet, the model will learn different patterns in the Reddit post versus the textbook snippet, and it'll learn to differentiate the task based on that instead of having a real understanding of what the task is, not just looking at pattern matching based on the structure of the data that's inside a batch. So here are the data sets, the kind of top 10 or so data sets by percentage mix. So Reddit is the highest percentage with 28% of the data, about 65 million data points. So these are, query document pairs or similar pairs. And then it goes down the list of different data sets with a decreasing percentage in the mix. They use a global batch size of 16,384. And I don't think it was in the latest version, but I was reading a previous version of the paper and they mentioned how a lot of their optimizations were targeted to get this global batch size because they had found that it was, performant for their purposes. For everything, they use a max sequence length of 2048, and this is their innovation of training only on 2048 tokens, but then allowing their model to perform inference on 8,192 tokens. They use something called grad cache, which I don't have a lot of familiarity with, and they used mixed precision training. Here is the loss between the query and the document. So this S in the exponent is the learned score. So it's the model producing embeddings for the query and the document and finding the cosine similarity score. And here at the bottom, they have the summation of the cosine similarity score between the queries and documents in the batch, where the document that's being compared to the query is not the target document, but it's the target document of the other queries in the batch. So this is where the in-batch negatives come into play. When I looked at this formula, the first thing that kind of popped into my head was, I'm like, oh, this looks like softmax. And I think that's kind of the concept here, is that you end up with a scale of 0 to 1. So that's stage 2. Stage 3, we get to supervised contrastive fine-tuning. And this is a much smaller data set. It's 1.6 million items of high-quality data. They mine for hard negatives for their retrieval data sets. And hard negatives are the top 20 documents that are not the target document. So they're still somewhat related to the query, and that's what makes them hard to distinguish as negatives. They again use this same source batch filling with data. They use 7 hard negatives per query document pair. And they also run an ablation where they train without the empty beard datasets to allow true zero-shot inference during evaluation to kind of match the expectation that the model is not trained on those data sets if it's going to be evaluating on those data sets. Here's the breakdown of those 1.6 million samples, where we have some retrieval data sets like MS Marco. And this was interesting. They trained for only one epoch, and they found that multiple epochs actually decreased the performance. And they found that randomly sampling the mined negatives instead of just picking the top, n number of negatives improved the performance, because when they were just picking the top n, they were getting false negatives. And now that we have the negative documents, the hard negatives, we have to introduce that term in the denominator for the loss. So here they modify the partition function, which is this denominator down here, to include h hard negative documents from 1 to h, where m is counting which document we're looking at, which are documents specially chosen to be close to D, but not true positive documents of Q. So I see this as introducing a kind of greater nuanced signal for the document, for the model to pick out the correct documents in a more difficult way. And so I think the idea there is that the model is getting better at discerning between kind of gradations of correct document. The overall training time was a single week on one 8 by H100 node. The masked language modeling, which is the training phase 1, takes roughly 4 days. Contrastive pre-training lasts 3.5 days. And contrastive fine-tuning takes 1 hour. So that last 1.6 million data set, fine-tuning takes 1 hour. And they noted to initialize from Nomic 2048, or their unsupervised contrastive checkpoints that are released under the same license. So just as an estimate, I was looking at Modal, and they have a single H100 for about $4 an hour. So if we take 8 of those and multiply that by the hours in a week, this is about $5,000 is the total cost, which is not nothing if you're, GPU poor, but in terms of the state-of-the-art performance that they're achieving, I think that's incredible. Okay, let's look at consistency filtering. So I'll go over the main concept first, and then I'll talk about a detail that I didn't quite understand. So they use a pre-trained model to filter out potential noisy examples. And the general idea that I understood from this is that they embed query document pairs, and then for a given query, they find the top 2 neighbors ranking by cosine similarity. And if the target document is not in the top 2, they discard that query document pair. And so this is trimming down the data set such that using a strong pre-trained model that's going to give you, good scores in terms of cosine similarity, or not good in the sense of like accurate scores, where the queries and documents that are a high cosine similarity, relatively speaking, are actually similar. If that model does not find the document in the top 2, then we're going to assume that that pair is just a faulty pair, or it's a weak pair, and we want to have high quality examples in our stage 2 and stage 3. The detail that I wasn't quite sure about is that they say we sample 1 million points from the data set, and for each query, and then da-da-da. So I wasn't sure how that 1 million points comes into play. Is that 1 million the kind of document collection that they're finding the top K from? I think that's what it is, but I'm not 100% sure. In some of the related work, they use a 22 million parameter model, all mini LM L6V2, and they found that it was discarding true positives. And so they instead use a much larger GTE base, which is a 109 million parameter model for that filtering. And they trimmed down from 470 to about 235. So they cut the data set in half. a detail that they added, which I thought was a really interesting, like nuanced way to think about this, is that when they use a cosine similarity threshold instead of the top K method that they described, they found that the quality of the retrieval pairs was lower when they were using this kind of universal cosine similarity threshold. So how I understood that was that, let's say they say anything lower than a 0.6 cosine similarity, we're going to discard. So, globally high cosine similarity or universally high cosine similarity. Now, in some cases, you might have the highest cosine similarity between a query and a document, even though it's the accurate document, the cosine similarity might be 0.4, but you've already discarded that. So now you've lost some of the retrieval items that were correct. So that was my interpretation of why that cosine similarity threshold versus top K2 by cosine similarity, that nuance difference made a difference in their performance. All right, so let's dive into some of the results. This is the first stage output of Nomic BERT 2048, and it performs similarly to other short and long context encoders when evaluated on the GLUE benchmark. And this was something I was not familiar with in terms of how the evaluation takes place for the GLUE benchmark. So they train for 10 epochs, and they calculate the test score on the test set. So this it's like a fine-tuning exercise followed by the test set evaluation. So that full process is what's considered the GLUE benchmark evaluation. Here we have the MTEB results, and I've highlighted up here, we have our unsupervised model. So this is our Nomic Embed text v1 unsupervised. So this is coming out of stage 2. And then for supervised models, we have our stage 3 1.6 million dataset item contrastive fine-tuning stage output. And then we have this ablated model, which was which had removed some of the datasets, and even though those datasets are removed, the performance does not drop that much. So I thought that was really impressive in terms of showing the generalization ability of a model not trained on related datasets. And then the kind of kicker punchline in the abstract is that these Nomic Embed models at 137 million parameters, which again, super impressive. I love anything that is a small or tiny model. When you look at the average score, as well as some of the intermediate scores, it's scoring higher than both of these OpenAI embedding models, where we don't know how many parameters there are. And it's competitive to the 7 billion parameter E5 Mistral, and it beats out the 4.8 billion parameter models that are listed here. So super, super impressive, 100 million parameter class model, really, really punching over its weight. These are the long context benchmark results. And again, it's outperforming the Gina embeddings v2 base, and it's performing similarly to the text embeddings Ada-002. So if we look at these averages in particular, it's outperforming Gina embeddings here, 48.5 to 44, and it's competitive with the OpenAI models. This is another long context benchmark called LOCO. And similar situation here, it's the best performing 100 million parameter class model. And it's competitive with the 7 billion parameter models as well. So if we look at the ablated one here, the average is 86.7, whereas E5 Mistral is 87.8. Something that was interesting down here is that the M2 BERT, which is an 80 million parameter model, is actually beating out the paper's 137 million parameter model. I'll just note something here where it says unsupervised model. I wasn't 100% sure what that was relative to, so I just want to point that out, that that might be a detail that I don't understand. Cool. So the last thing I wanted to go over was the dynamic NTK scaling. And I am not super familiar with rope embeddings. I have, read a couple blog posts. There was a really nice Luther AI blog post on rope, and that definitely gave me a better understanding, but by no means would I say I'm an expert or super comfortable with it. So I'm just going to look at this at a high level and try to take away the high level items that I can from it. So this was really interesting. There was actually a Reddit post that they have linked at the end of the technical report, where this Block 97 user has done this analysis on modifying the llama rope class with a few lines of code. And the main idea here is that you're trying to run inference on some longer sequence length L prime, and L is the original sequence length. So, in our case, it's 2048 for the Nomic embedding models, and L prime is 8192. So 8192 divided by 2048 gives you a factor of 4 is your S value here. And so you're rating S by exponent value that's just very slightly above 1.0. So let's say our dimension is 512. So 512 over 512 minus 2 is 510. So I think that's like 1.004. So this is very, very, very small exponentiation just above 1. And what that does is that it makes this like very smooth, very gradual scaling. And it was, if you go to Desmos and you plot this, it's basically a vertical line, but the change is there. So it's interesting to see that such a small change in our base value of theta is creating a significant enough difference that you can use a longer context window for your model. So if we look at the code, they have a value of 8. So this is different than what they use in the paper. They use a alpha value of 2. You have your base theta multiplied by a raised to the power of the dimension divided by dimension minus 2. And that's it. But that alone is sufficient to allow a 4x context window increase or difference. And that's how they can get the 8192 tokens. So this is NTK aware scaling, and it's kind of the concept they build off of. The actual scaling they use, the dynamic NTK scaling, is this function here. And it's similar. You still have this S value, which is the L prime over L. You still have your dimension divided by dimension minus 2 value. So that, is that very slightly above 1.0 exponent. And then you have this alpha value that you're tuning as a hyperparameter, and they set their alpha value to 2.0. And so here you have 2 times your S value is 4, so this is 8. 8 minus 1 is 7, and 7 to the, whatever this power is based on the dimension times your B gives you your modified theta. So I'll just highlight here, it gradually scales the embeddings as sequences grow longer, preventing abrupt performance degradation. And that gradual scaling is very, very small. So that was really interesting to see how such a small difference can impact the performance in such a big way. So I'll end again with my main takeaways. So the biggest one is that this is the first fully open weights, code, and data state-of-the-art embedding model. It was trained in 3 stages. The consistency filtering approach cut the training compute in half, basically, because you're using half the data set to train, and it's higher quality. They found that top K, even though it's using cosine similarity, is better than a universal kind of flat-out cosine similarity threshold. Their contrastive fine-tuning uses in-batch and hard negatives, and so you introduce those in the denominator of the loss function. They use single source batches to prevent the model from hacking it with source shortcuts. So it's learning the actual content and behavior of the task. It's not just learning patterns of the differently structured data from different sources. They use task-specific prefixes to improve model performance. So you could have one situation where you want to find a similar sentence to your query, and another situation where you want to find the answer. And those are two different situations, and the model needs to understand that those two are different situations, and it does so with this additional token. I kind of understood that as like the CLS token in BERT, where it's kind of learning some kind of average aggregate value that represents the entire sentence. That's not explicitly mentioned here, but that was my interpretation. Another big takeaway that it outperforms the OpenAI models on short and long context benchmarks. The long context is achieved even though it's trained on context length that's 4 times smaller, or 1/4 the size rather, because they're using this dynamic NTK scaling. And they're using modern optimizations like rope, flash attention, and swigglue to improve training performance. So that's it for my technical report summary presentation. Really interesting paper. It's really inspiring anytime you see anything coming out where a small model beats a large model. So I was super excited to read this, and thank you for watching. I'll be doing more research paper summaries. I already have a playlist going if you're interested in that sort of thing. Thanks for watching, and I'll see you next time.